It is recording now.
It's also fun because we're trying to get Gregor to do it. But, he said, I'm still doing data, so if it's a good spot, I can.
I think we're good for now.
Yeah.
What are we going to grab? Or what are we trying to grab?
A monitor.
A monitor? What for?
Servers.
Oh.
As it turns out, setting up networking over SSH is not a very good idea. So we accidentally broke it.
Okay, that's all right. You guys can borrow the ASAP monitors for a little bit. Yeah.
Oh.
Okay.
Can you bring it after the
Yeah, you guys can get a monitor
Yeah.
for like $80.
Yeah.
Right, so
yeah.
possibly not.
Can you bring it out at like 2 the Vulture place?
Yeah. Okay. Yeah. Is this recording? Awesome. All right. Yeah, sorry for the slow introduction, but all right, so we're going to talk about singular learning theory. What the heck is it? Why is it important to learn it? And how does it relate to your current understanding of machine learning models through things like mechanistic interpretability? So,
move the
of course. But how do I do that? Yeah, we also should. Awesome. So what the heck is learning theory, and why should you learn it? And so we're doing learning theory, and we're learning theory. So it works both ways. But okay, so what is it, and why is it so important? Actually, maybe I should turn down the lights, or is this good?
Yeah.
Okay. So you can kind of think about this as an analogy to developmental biology. So if MechInterp was understanding organisms at the levels of cells and structures, learning theory is understanding organisms as they grow. So we know that the structure of a model after it's been trained depends very heavily on both the trajectory it takes as it grows, its learning process, as well as the loss landscape, which informs the learning process. So if you guys want to visualize this, think about like a triforce, basically, where the corners of like the triforce, you have model structure, you have like model trajectory, like the trajectory it takes in weight space as it moves to where its final destination, and then the loss landscape. All three affect each other, and like learning about the loss landscape can tell us a lot about how the model will perform as it's like training, and also what it'll do once it's finished training. So here's the disclaimer. There are literally textbooks on statistical/singular learning theory that dive into the math. I'm not going to dive into the math because the proofs are quite lengthy. Like these books, like to understand singular learning theory, these are like the introductory readings. And singular learning theory is based off of this theory by Sumio Watanabe, which is this Japanese researcher who's been working on algebraic geometry for 20 years now. So it is quite dense, and I'm not going to go into the proofs. So basically here, I'll just kind of distill the intuitions from singular learning theory. But for the proofs, if you guys want to know why, there are books on it. I don't think I could explain it to you if I wanted to, because I don't have the background, unfortunately. But I'll do my best to kind of give you guys the results of these proofs. And in the end, I think maybe it'll still be valuable that way. And if you guys like math, here's a lobster. I hope it's a good consolation. All right, so just to give you guys some motivation behind understanding learning theory. So here's like the puffing demo. So here's like the first steam engine in 1801. And it was like the first steam engine, and it was 40 years ahead of its time, or 40 years ahead of the widespread adoption of steam engines. And I think if you lived in 1820, before the general onset of steam engines, it would be hard to predict whether this is just like a curio, or whether this would actually like power the Industrial Revolution. And basically the way that you can kind of predict whether something will grow huge or not is if you know that like there's like some general principle that will allow them to like scale really well. Like for when the puffing demo was created, it was basically just like a curiosity. Like there was no established theory of like thermodynamics that could show that like you could just generate energy using heat engines. But then like after the adoption of steam engines, empirically we figured out that okay, like these steam engines can be quite powerful. What's their theoretical limit? We we went through thermodynamics and we created like a theory of general heat engines. And then afterwards, we're like, oh, there's actually like the theoretical limit for steam engines is quite high. So we can just scale steam engines until the theoretical limit. And so this is generally how technologies develop. You can see here on the very right, there's a steam engine used in the factory. It's quite a large steam engine. And then there's like also steam engines used in coal mines, which was actually it was a really key piece of technology because you need coal to like power steam engines. And you can also use the same steam engines to ventilate the coal mines and also to draw out water from the often like sub-waterline coal mines in England. Anyway, but like basically, in order to know that whether like something happening in our age, for example, deep learning, is possible to like scale to widespread adoption like that, we'll first have to see whether there's like any theoretical bounds on what we can do. And so like basically these technologies are called GPTs or general purpose technologies, nothing related to the general pre-trained transformers. Yeah, I know, it's a horrible, this is actually what's used in the industry. In like the scientific analysis like literature, they actually call them GPTs. And examples of GPTs are things like the steam engine, electricity is a GPT, the internet is a GPT. And GPTs might also be a GPT. But usually the trend is always that like first technology starts off empirical. Empirically, we find that technology is useful before we start developing the theory, and then we test and establish the theory. And then after theoretical laws are established, these general purpose technologies scale until we approach their theoretical limits. And so yeah, so for example, electrification is a GPT. We've largely reached like we're almost at the limits for things like transformer efficiency, like electrical transformers. So yeah, like generally technologies mature until they're near their limits. And right now we're in what's so-called the handcrafted era. We're still in the handcrafted era of neural networks because we kind of like do stuff by trial and error, and we just like figure out whether things are good by testing them. And this is largely because we don't have like a well-established general learning theory, which might be easy to, well, it might be good to establish. It might be possible to establish, I should say. And also, if it seems like model learning theory is like really chaotic today, just compare it to like 1820s thermodynamics theory. It was like not well established. It was also equally chaotic. Share of horsepower electrified. So like in the lumber industry, like more and more of the lumber industry is electrified as opposed to like powered with coal or horses or something. Yeah. Or electrified not as in like shocked, but like powered by electricity. Yeah. And then, oh, with it? Oh, petrol. Yeah. Interesting. Yeah, it does seem like there was a dip in like roughly 1945. No, this is a share, so I guess we use less electricity to power petrol. Yeah, that seems strange.
So the share of coal,
I guess other than using electricity, they could use steam power. That does seem like the other alternative.
Or
Just more labor in the coal mines.
yeah.
like the
Just grab a pickaxe. Yeah. No need for electricity. Anyway, so why do we establish this theory? Well, at scale, trial and error is not an option. It gives you the courage to kind of just go and scale. So there's this paper that was published before GPT-3 was trained, and it was called Scaling Laws for Neural Language Models. And you can see the key graph on the right. And it was a paper by OpenAI where they just ran a bunch of experiments around seeing whether transformers could actually hold up beyond GPT-2 scale. And it showed that it did. And then OpenAI cited that paper as a reason for them to take the $1 million dive to build GPT-3. So if you have these theoretical guarantees about model performance, then it gives you the courage to really try and build something. Like if you know something is theoretically possible, then you'll be more driven to actually put that thing into existence. And also, you really don't want to be running experiments and seeing if things like work or not when you're dealing with million or billion dollar models. Also, theory tells you which types of models are promising and which types of models don't work at all. If like a type of model, like if you're researching into a new type of model, and then the theory tells you that your model like will never reach the optimal that like transformers are, then maybe you don't want to pursue this line of research anymore. And so what it tells you is you can kind of rule out avenues of investigation before trying them. So it gives you the ability to focus your experiments on more targeted areas. And then it also establishes theoretical limits. So it helps us answer the question like, will human level intelligence be possible from deep neural network scaling alone? Or will there be like more fundamental limits that will need to pursue a technology other than deep neural networks to get to human level intelligence? And also here's like the AI safety why. So as I mentioned in the mechanistic intro paper, AI safety is a pre-paradigmatic field. So again, there's no consensus on how to approach or study model alignment. And there's the idea that like if you have mathematical guarantees about model performance, then maybe you can do things like you can inform policy a lot better. So you're like, if you have theoretical guarantees that like a model of a certain parameter count will never exhibit like certain capabilities, then you could like create legislation to like limit basically open source models to like that parameter count or something like that. And the ideal case for AI safety is that you can also put similar mathematical guarantees on what a model will do, other than like what loss a model will reach. Well, obviously this is like a little bit ahead of where we currently are in research. Right now, most of our proofs are like not extremely solid, and we only have like hard proofs for like certain neural network cases. But we do know that like the things that we learn from these cases translate a lot to other neural networks. Here's the comic again. So yeah, so here's how we train neural networks today. We have like a bunch of linear algebra. We like stir it in the pile, like, and we just take gradients until we take like these little gradient steps until our linear algebra starts doing the things we want. But what exactly is going on? What exactly does the loss spacing look like? Like how exactly is our matrices like moving in this way that like makes them perform what they perform? And like, can we think of this as like maybe a search process, or can we think of this as like an annealing process maybe? And actually, if you look at the math of singular learning theory, they basically tie in thermodynamics with model stuff. So later on, I'll introduce this thing called the Watanabe free energy, and we'll see that like inside the Watanabe's textbook, there's a really funny line that says gradient descent is tantamount to refrigeration. You're basically like cooling down your model until it anneals in like the best spot. And I don't have the I don't have the mathematical background to verify that his proofs like correlate with that statement, but it does sound right. So anyway, yeah. So to get onto the material, here's the deep learning data regime. So when we have like small data regions, then like the best guess error is like basically the best guess you can get, the best model you can get out of just using statistics. So like the mean variance, like model, like human engineered statistics, stuff like that. And here's an irreducible error. So here's like the error you can never get better than without overfitting. This is like just like human label noise or something like that. And we have like these three regions of model scale basically. We have the small data or data scale, I should say. So we have a small data region where you can't actually get much better generalization performance than you can through statistics. There's a power law region, which we're currently in, where we can get like significantly better generalization error, and we have not reached the irreducible error region. The irreducible error region actually depends on your data set. So different data sets will have different amounts of irreducible error. It does appear that for some data sets like ImageNet, we actually might be getting close to the irreducible error like domain. But for most like language tasks or whatever, we're not quite there. So let me just talk a little bit about like the three eras. So the first era is the small data era, so before 2010. So the scale is too small to see the wide advantage of neural networks. So because neural networks can't really get much better generalization performance than things like naive Bayes or decision trees, actually neural networks were not great. They were more computationally expensive. Now we're in what's called the big data era. So there's like sufficient scale to see performance on many tasks. And yeah, actually now we moved into the power law era. So actually the big data era is like a little bit around here. So now we're like sufficiently in the power law region where we have like predictable scaling laws. And this like trend line becomes roughly linear, like according to the log scale of the training data size. So actually sometimes I talk about like model scaling laws. Like what exactly does a scaling law look like? Well, here's a scaling law that like keeps model size roughly the same. And all we're changing is the data set size. And we'll see how the loss scales with the data set size. So if you guys aren't familiar with this symbol here, it means proportional to. So the loss of the data set is proportional to the size of the data set to the exponent of negative 0.095 roughly. And basically, this is a really bad scaling factor, but it's very common. So to decrease perplexity or like log loss by 5%, we need to increase the data set size by 2.72 times. That's kind of a yikes. But actually, what you might want to note is that even a 5% decrease in loss could lead to pretty big downstream task benefits. It could mean like a large capability boost. So Note that the exponent of d is actually the most important term here. So you know that the loss is proportional to some constant times d to some power. And the exponent is like really, really important. Let's call it gamma. And it's linearly related to the percent L decreases for every doubling of d. So if gamma is much larger, like let's say gamma is twice as large, then the proportion that like L will decrease will double for every doubling of d. I'm not really sure if that like gets across the intuition here, but basically the exponent is like really, really important. It's like the asymptotic term in like time complexity analysis almost. Like you really want the exponent term or gamma to be as small as possible or as negative as possible for your model to scale really well asymptotically. And we know that different architectures change the constant factor in front of d. Gamma almost never changes. It's really, really hard to change. We know that inside deep neural networks, different architectures roughly scale with around the same exponent coefficient. So if you guys are familiar with how like LSTMs, when scaled to GPT scale, will also perform nearly as well as GPTs, that's kind of what I'm talking about. It's just
really?
Yeah. Yeah.
Damn.
There's a paper about that. I don't remember the name, but our team might know it. But yeah, same with Mappa or something. It's just like certain architectures are like more computationally easy to train because our hardware accelerators are better suited for them. Yeah, Leo.
So is there any reason to believe that no model architecture will change gamma, or is there a theoretical reason gamma is very hard to change?
Not really.
So the only thing that actually do like material changes
Yeah. The other thing that changes is how easy it is to train a model. Like transformers are parallelizable, so like it scales better because it's like our GPUs are parallel. Like, it was. It had like a special name. I think if you search up R and N scale as well as transformers, it might be a paper that comes up.
and in these cases, when they, I assume these are experiments that were built in do they like keep the type of loss they were training on the same, or just like for a single task, no matter what loss you come up with, no matter what like let's say we're completely comparing gas and energy models for completely different paradigms, you still have that number.
No, this L is is specific for this loss formula.
Oh, okay.
That's just
So the
negative,
loss.
negative log loss. Yeah.
Oh.
Yeah, Leo.
And I assume there hasn't been any tells us the gamma for different loss functions.
Not really. This is just the formulation I found. I think you can probably find some other stuff, but the most, like the architecture we're most interested in scaling is the transformer architecture, and almost all of them use like perplexity, which is the negative log loss. Yeah, RT, did you find anything? Was it called GLM or something? No, I don't think so. Okay. Actually, don't quote me on that now, but I could have sworn I read it. I'll search for it afterwards. If I do find the paper, I'll let you guys know. Yeah, but like empirically, a lot of different architectures. Like if you look at spin transformers versus typical transformers, there is like there's slight modifications of how efficient they are, like the constant factor. But generally, they scale like roughly if you double the size of the data set, it'll increase loss by like 3 or 4%, decrease loss. Sorry. This is general transformer like scaling law. No, oh sorry. The only thing we're scaling in this case is the dataset size, so we're keeping everything else constant. Oh, that's just derived from the formula above. No, I just did the math. You can take the log of both sides and you can calculate it. Yeah, yeah. Assuming a negative 0.09 is a scaling factor. Yeah. You can find the chinchilla paper. If you take out all the factors aside from the dataset scaling factor, and you look at the like you keep everything constant and you just look at empirically like how model performance scales with dataset size, this is roughly what you'll get. This is from, I think this is from like Watanabe's book, if I recall. It's just like there. So yeah, anyway, let's like kind of assume that this is true. And like this is true for the case where you use negative log loss. And generally we can formulate the loss given dataset size as a function of dataset size as some lambda times d to negative gamma. And so we want gamma to be as large as possible because that means that the loss will go down faster as you double the datasets. So that's great. Anyway, so here I just wanted to show you guys that like even a small decrease in loss can yield large results in bad downstream task performance. So this is a paper Tina and I read. So here's like scaling loss or downstream performance. On the top you can see the blue score given the number of tokens, and at the bottom you can see the loss for the number of tokens. And so if you look at the curve right here, even though the loss doesn't decrease very much, the blue score actually increases significantly. And so it is the correlation is a little bit less like one-to-one between how the loss decreases and how your downstream performance will increase. But yeah, like sometimes like even like small decreases in loss, especially when you're like almost at the boundary of irreducible error, can really like increase your model's capabilities. So 5% is nothing to scoff at. So let me talk a little bit about the traditional like classical ML before we had deep neural networks. So it wasn't always this way. It wasn't always that you can just scale models to like really large sizes. In fact, this would have been extremely strange to people in the traditional statistics industry. So you guys have probably seen this graph, right? In M146, C147, you have like an underfitting like decision boundary, and you have an overfitting decision boundary. And in statistics, we're like, okay, so like let's say we have some data set and we have some model class that we fit the data set. Generally, we'll see that like if our model class complexity is too low, then we'll underfit. If the model class complexity is too high, it'll overfit. We have 5 points, and then that's like a fourth degree polynomial, and you can see that's almost overfitting. And we'll know that like if we have even more, like if we have a much higher degree polynomial, like a 100-degree polynomial, we'll overfit beyond measure. Like our thing will just not take on any reasonable values for any data points that are outside of the data distribution. Like it'll generalize extremely poorly. And that's just like the typical statistical like framing. And like I think if you told a statistician back in like 1990 that you could just scale neural networks up to like billions of parameters, like if your neural network has more parameters than your dataset has tokens, then they would be extremely confused as to why it would generalize. And I'll kind of explain a little bit why. So here you can see in this image here, you can see we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points, and then the 9th degree polynomial. Generally, in order to specify an nth degree polynomial, you need n plus 1 data points to uniquely specify an nth degree polynomial. And if you have fewer data points than you have polynomial degree, then you'll just have like a polynomial that goes totally wild, and it will make no sense beyond the bounds of your data. And this is like kind of expected behavior if you think about it, because your polynomial is underspecified. Like your data points are there to like hook the polynomial in place to specify the polynomial. And if your polynomial has a degree greater than the number of data points you have -1, then your data set cannot uniquely specify the best fit polynomial. So there are many possible polynomials now that could all fit your data set perfectly, and the vast majority of them don't generalize because the vast majority of them, like because your polynomial has the freedom to do whatever it wants on the areas of the data of your data, like between your data points. And it just seems like the majority of polynomials that can fit all your data points would like do extremely poorly on the intermediate like periods between your data points. So yeah, so let me formally specify the counting argument. There are like infinitely many polynomials of order equal to or greater than the number of data points, which interpolate the training data perfectly. And almost all such polynomials are terrible at extrapolating to unseen points. And this is from a textbook, Pattern Recognition and Machine Learning. I think it was published in like 1990 something. And so like, why is this not true anymore? Like, isn't it true that like if we have a neural network with like 1 million parameters and we have like 10K like training samples, like shouldn't most neural networks be like extremely terrible? Like anyway, so like analogously, neural networks that generalize have to implement very specific functions. Neural networks that overfit are free to do almost anything on the unseen data points. And modern networks are hugely over-parameterized. Or in other words, the dataset cannot uniquely specify a model that fits them perfectly. There are many models that fit each dataset perfectly. So there should be way more neural networks that overfit that implement specific general algorithms. Are you guys convinced by this argument, or like you guys get the general gist? Guaranteed? Yes. You can think about this in terms of bits information, or I guess you can think of it like that, like bits information. But we do know that like neural networks don't do terribly, even if you have like way fewer data points. Like if you train like something on an MNIST dataset of like 100 images, and your neural network's like 5 million parameters, like even if you count the number of pixels, it's going to be less than the param count, and you still get some degree of generalization, especially after grokking. And so I'm going to kind of like poke a hole in this argument later, but I just wanted to make sure that this argument seemed kind of sensible. Okay, so here's like the statistician's argument here, the count. You guys know if there's like water outside? You think I'm allowed to just like steal? Okay, okay. One sec, I'll be back. Awesome. Okay. Here's the weight space argument. So here's like the generalization of the argument for neural networks. So models occupy weight space because you specify a model by its weights. We can model the optimization process as locally greedy search over the weight space to find parameters that minimize loss. So you start somewhere in weight space and you traverse weight space. You just like move along it until like following the gradients of lowest loss until you find the local minima. And so out of all the possible models in weight space that minimize train error, what proportion of them generalized have low test error? And so that is the question we're dealing with. So if it turns out that most possible models in the weight space that have low training error also turn out to have low test error, then it is not a surprise that models generalize. But if it turns out that like most models in the weight space that minimize train error have high test error, then it really is a mystery as to why models generalize. And so here's here's a paper that that kind of looked at this. And what they did was they added some poisoning. They added another coefficient, like another learning coefficient that like encouraged a model to do poorly on the test set. So as part of their loss, it's like minimize loss on the train set minus loss on the test set times gamma, where gamma is the weighting factor. It's not a test set if you're training on it, right?
Yeah.
If you're receiving signal from it. But it's like very clear to see that like when gamma, I think this is like when gamma is like 0.01. Like basically, this is for a binary classification task. So we can see that when you try to minimize performance on the test set, you can get like low accuracy. So like basically all these models do very well in the train set. I think this is a UMAP where. Yeah. Yeah. And so you can see like beside the path, there's like we're basically carving a path through a sea of models that like all perform very well in the train set, like perform equally as well, but like perform really poorly on the test set. Like this is like worse than random, right? So it's like it does seem like we're just like parting the seas of like bad models and we're just like sticking to the path of models that generalize decently well. Yeah, I think that's true. I think what this paper is trying to show is that there are like the argument that like a network that does good on train should also do good on test is like mostly false. Like there are many models that do very well on train and do very poorly on test.
So the path is the models that do exactly that, or is it?
Oh no, so this is like a training path. So here are like perturbations off, like basically they fork a model off the training path, where they add like the gamma regularization.
I see.
Yeah, so you can see like it's actually not too far, or I guess this is like a UMAP visualization, so it's hard to know how far it is. But there's like a lot of models that like can memorize the train set. So it shows that like at least these models have no problem memorizing the train set, and yeah, it's just like generalize very poorly. And it does seem like you need a particular kind of model that implements a general algorithm in order to work well on the train and test sets. So like the question is, maybe like what proportion of weight space is like filled with models that are good, like generalize well. Like let's say you have like a loss landscape and you set a minimum like train loss threshold. So you like set like a bar basically, like a plane dividing the loss landscape, like a horizontal plane, and you're like, okay, I want like if I have a model with train loss below this threshold, how many models exist? Like what volume of weight space is filled up with models that memorize, and what volume of weight space is filled up with models that actually implement the general algorithm? And then maybe if you knew this volume, you would knew like you could solve this mystery. Maybe you're like, okay, most of the weight space is actually filled with models that do really well. Actually, the thing I'm going to show you is that most of the weight space is filled with models that like totally memorize. But what actually happens is that there's like a big attractor space. There's like a big attractor basin around the area that like generalizes really well. And because we always follow the gradient, SGD will kind of pull in the model towards the attractor space. So I'm gonna, before I introduce the loss landscape formulation, I'm gonna talk about double descent. So this is a behavior that might be extremely strange to you guys. So basically this is an OpenAI paper. They keep everything the same. So they train all the models on 4,000 epochs, enough to overfit on the same dataset, and they just increase the model width. And here's the test error. So they actually, yeah, they plotted both the train error and the test error on the same plot, but purely plot the train error. But anyway, here's the test error. So you're like, okay, models that are like very small, as you increase their size, their test error decreases. But in like this certain area, like as you increase the model size, the test error increases again. And then beyond this threshold, scaling improves test error again. So it seems like there are like three different regimes. There's like the model is really small regime, where making the model bigger helps it implement more complex algorithms that fit the test set better. There's the model overfits the train set regime, where it just memorizes on the train set. And there's the model seems to generalize for whatever reason, where it's like hugely overparameterized, but like improving the model size also improves its performance on the test set. And so this behavior is called double descent, where you have like descent number one, descent number two. And actually, what this is really interesting. OpenAI makes this claim that like this trend is expected to like if you use modern ML scaling laws, it would predict this curve. And then if you use classical statistics, it would predict this curve. Like for example, if you try to fit a polynomial, it would like its test error would increase as the polynomial degree increases. And so like there's like this boundary area where like expected like the classical statistics and modern ML kind of clash a little bit, and then test error increases, but then it decreases again. Yeah. So it's really cool. So why does this happen? This is like a big problem. This is like a big question. And OpenAI coins this term. So they coined this threshold the interpolation threshold. And they say this interpolation threshold happens roughly at the point which the model is complex enough to fully fit the data set. They don't rigorously define this, but I think in their paper they say this is somewhere around the area where like the model has roughly as many params as the data set has samples. So it seems that like roughly as the model, like so in this regime, this area, the model is not complex enough to fit the whole train set. It's just like too simple. And right at this point, the model, like when it has maximum test loss, that's when it's just able to fit the train set. It's just complex enough to like fully fit the whole train set. You see train losses though. And then as it becomes more than complex enough to model the train set, it starts showing.
Happens. Also,
This is not training epochs. This is model size. So like this is model size trained on 4,000 epochs on the same data set, on small data set. It converges, yeah, it like doesn't get there. No, it's generalized. So like actually you see this double descent not only on model size, but also with training steps. So I said like like basically when you get training steps to a really high number, this is kind of like grokking, right? Like, I'll show you a graph on the next slide actually. So you also have epoch-wise level descent. So here you go. So actually the color here, it's obscured by the zoom bar a little bit, but the color, like the more yellow it is, that means like the more high the test loss is. And so like let's say like a big model, as you train, like your test loss decreases. And then after you train it for like a bunch of epochs, the train loss increases again. And then as you train even more, the test loss decreases again. So here's like roughly the grokking phase. So you have a big model, right? And like it implements like some algorithm, and then it like has low test loss, and then its test loss like I guess it stays the same or increases, and then after it like does grokking, the test loss drops once again. But grokking happens at like a very high epoch number, so you can see it's like 1K epochs or something. Yeah, the thing is, like, you might not observe this in your own models. It might be because your models are not big enough, or you haven't trained it for enough epochs to like reach like the double descent phase. Maybe you're still in the first descent phase. I think it's also possible you have seen the first descent phase as well as like the ascent phase, and you did early stopping or something. I actually don't know. But like OpenAI published this paper, and it has been replicated, so I think it's probably a real fact. So I just posed this question, like this does seem very confusing, and I don't explain why it happens. So I just want you guys to keep this question in your mind, like this mystery in your mind, as I go into loss spaces. But yeah, so let me just kind of describe the graph. So here's the test error as a function of model size and train epochs. And so here's the model-wise level descent. So you can see as the model size gets bigger, here like the test loss decreases, and then it increases, and then it decreases again. And then you also have epoch-wise level descent. As you move up on the graph, as you train more epochs for the same model size, the train loss goes down, then up, then down. Well, let's say you're a low number of epochs and your test loss starts going up. Maybe what you do is you actually let it train for 1,000 more epochs, and then the test loss will go back down again. Yeah, Leon? The interpolation threshold doesn't actually look like it's happening at any particular loss value. You can see the interpolation threshold here happens at higher loss values than it does it here. So yeah, but it does seem like it happens at, later on you'll see that it happens at a certain model complexity, or you'll see that there's like a coefficient that reaches a certain value when you reach this threshold. Anyway, yeah, so here's a third kind of double descent that you see. Here's test loss, and here's the embedding dimension. And then as you scale the embedding dimension, you'll see the test loss goes up and down. Actually, yeah, so it's also true that as you scale the data set to be larger, like for a given model of a certain embedding dimension, it might actually be better to train a smaller model, or like to train it on a smaller data set. This is the same paper. So search up OpenAI double descent paper. 2019. Yeah, so this is before the single learning theory work. So I wonder if I can decide actually. I can do this. Okay, so here's a hypothesis posed inside the paper. So they say that for any natural data distribution B, neural network-based training procedure T, or tau, and small epsilon greater than 0, if we consider the task of predicting labels. Yeah, so it's like basically 3 regimes. There's an under-parameterized regime, there's an over-parameterized regime, and there's a critically parameterized regime. And in the under-parameterized and over-parameterized regime, we can expect test loss to go down as like models become more capable. Like they either become trained more or they become of a higher complexity class. But in the critical regime, anything goes. It could go up or it could go down. This is like, yeah, this is in the paper, and they use a lot of math. Basically, they just say that there are 3 different phases. And so let me kind of give a potential answer to this mystery. And so I'll talk about loss basins. And so how many of you guys are roughly, or I guess I'll just explain the loss landscape, but it is possible that many of you guys are familiar with this formulation. But what a loss landscape is if you plot, for example, this is like one parameter, this is another parameter, and then this is the loss, you can plot this nice landscape. And you can see how the model weights traverse the loss landscape over time. So usually you'll take the gradient with regards to these parameters, and then you see the loss decrease, and it'll move in the same basin. And very frequently, we will see loss basins illustrated like this. They don't look like this. They don't look like this because A, they're very high dimensional, and B, they don't look like this because they don't have this nice smooth curvature, which I'll show later on. So yeah, ball rolling downhill is not necessarily accurate. We plot the weight space against L. So the weight space is usually very high dimensional. So the dimension of the weight space is the number of parameters of your model. And in this case, it could be billions, right? And so let's say you have like a billion dimensions plotted on x1, x2 to like x a billion, and then you have like a z-axis. And recall that volume scales to the power of the dimension. So let's say you have like some pit. Let's say you have like a pit over here, and the volume of the pit in R2 in this case scales with, or I should say, like, we don't care about the volume. We care about the radius of the pit in R2. The radius of the pit scales with the, the area of the pit scales with the square of the radius, right? Yeah, yeah. But like, let's say you have like a billion dimensions, right? And you have like a pit in a billion dimensions, and then you have like the volume of that pit of the attractor space that like leads into the pit is radius to the power of a billion. And so what does that actually mean? That actually means that basins in high dimensional loss landscapes that have smaller radii are like infinitely smaller than loss basins with larger radii. And even like a small change in radii means that like one loss basin has like a huge volume compared to another loss basin. And so what we would expect to, what we like theoretically expect to find in loss landscapes is usually the models will roll into like the biggest loss basin. Because the biggest loss basin, let's say like the radius is like normally distributed, the biggest loss basin is probably like, I don't know, like 1,000 times larger than the second largest loss basin in terms of volume. And so it's just like very likely you'll get drawn into this attractor space because one attractor space is way larger. So yeah, loss basins are, so I say here that if loss basins are roughly convex, then loss basins with larger radius will have many times more volume than smaller loss basins, but loss basins are not convex. We'll see there's actually a term that caused loss basins with larger radius to have even more volume than smaller loss basins, even more than their normal like volume formula would show. So one thing to pique your intuition here is the flatness criterion. So in many papers, we observed that algorithms that generalize better occupy regions of the loss landscape that are flatter. So here's a very good model. It performs very well on the training set. It like reaches 97% accuracy on test set. And the bad minimizer, we show, if we plot the local loss landscape around it, we show that it's in like this weird divity pit, and it does very poorly on the test set. And I think this is a trait that M missed. It's like basins that are wider occupy dramatically larger volume parameter space than sharp basins. Oh yeah, so here's like kind of the explanation to the mystery about why general solutions tend to be the ones that models actually end up finding. It's because because general solutions have like smoother gradients around them, they tend to have larger radii. And because they have larger radii, they have like dramatically more volume than like these little divity pits. So maybe the number, so like maybe even like the total volume of models that actually like sit at the bottom of these loss basins is small. So maybe there are like a lot more, there's like a lot more volume maybe in models that like achieve high train accuracy while achieving low test accuracy. But if you look at the whole basin, the whole attractor space that leads the model to fall into the pits, actually these basins are a lot wider because they're less sloped. They're like broader. Yeah, sure, sure. So let's say that like inside our lost landscape, there's like a lot of these narrow pits, right? And there's like one huge basin. The if we just look at the part of the lost landscape that has low training loss, it'll just be like the very lowest parts of the lost landscape, right? And so if we look at the very lowest parts of the lost landscape, maybe there's like usually a lot more volume in the pits than in the broad basins. Because we only look at the volume at the very bottom of the basin versus like the very bottom of the pit, right? But if you want to look at like where the model is likely to be randomly initialized, it's way more likely to be randomly initialized near like a lip of the wide basin than of the narrow divot. So it's way more likely to fall into this than fall into that. the same depth. Yes. Uh, Roughly the smaller basins implement like memorization, so you memorize the training data. But if you might imagine, like memorizing training data is very sensitive to your exact weight. So if you vary your weight a little bit, then your memory will be wrong, and then you'll just like misremember part of the training data, and your loss will be much higher. But if you implement like a general solution, you can imagine that there's probably like a lot of similar weights. Like if your like general solution is a little bit off, then you'll get something that's like almost right, but not quite. But like the reason why like the bottom of the pits and the bottom of the good minimizers have like the same loss, we assume that like the model is over parameterized, so it's able to get zero loss on the test on the train set. Sorry. So if it's over parameterized, then there'll be a lot of like these areas with zero loss. Yeah. Because of the loss, the larger basins implement general algorithms, while the smaller, narrower basins implement like specific like specific minimization.
Well, you're not necessarily disturbing your weights, but you're more modifying the loss function. Because if you think about like evaluating a model or like training a model on a test set and training a model on a test set produces two different loss landscapes. But the idea is that if these data are similar enough from a similar domain, the loss landscape should look similar. But if your loss landscape is sharper, like if I find a really really sharp minimum, then that means on the trained data set, but on the test data set, that very sharp minimum will not exist, right? Yes, but if you have a really big general sort of like minimum, then there's a good chance that on your test data set, when you evaluate on that, the loss landscape will also have a larger. Yeah.
Imagine like what is like I think Jordan's like basically getting at like basically the test landscape is like very similar to the train landscape, but it's like a little bit different. And then if it's like a very general thing, then if like the test landscape is like a little bit different, no matter, it's still a problem. You're still likely to be like at somewhere with low loss. But like if this is a little bit different, like this is usually like way narrow, right? Like you're just gonna likely hit like a limit or something with like high loss in the test landscape. Oh yeah, so this is a paper on how batch norm works, or sorry, no, this is a paper on how skip connections work. But basically, here's a landscape without skip connections. You'll find that like it's really hard to navigate down this landscape. But skip connections make the lost landscapes move.
Because
There's like a direct connection of there's like gradient flow directly towards each weight from like the end. Yeah.
people have an argument who I read for a long time, and like this was one of the first arguments that like skip connections makes the loss landscape smooth, and like we can show it because we can just train one and be like, hey, look, your eyes. But like I think later there's some people who made other claims to be like, well, the loss landscape being smooth is the result of some other thing, and it's like,
That's interesting.
yeah, but yeah. Yeah, the identity being that you can basically learn a shallow version of the network first, and shallower networks, because they're less complex, generally have not as jagged loss landscapes.
The way I've heard it like described is that your deep neural network kind of becomes like an ensemble of many shallow networks. And because you're kind of like overlaying the loss landscapes of shallow networks over each other, they kind of smooth out on average. Um, and yeah, generally inside like ResNets, we do find ensembles of like shallow networks that are like maybe 13 layers deep or something like that. So, but yeah, it's like this is like a flatness criterion. So maybe like this demonstrates a reason why. And actually, singular learning theory demonstrates more than that. So, oh yeah, so here's a really good paper. It's where all these illustrations come from. But basically, we can see like they empirically show that when they train a deep neural network on this Swiss roll dataset to like learn the decision boundary, you see when the very general boundary happens, the very general boundary has like a very broad basin. And then when the very sharp, like you can see this achieves perfect train accuracy. But you can see that these are very jagged. It's an extremely narrow loss base. And the way they're doing these visualizations is they're doing a two-dimensional cutaway of like the, for example, 1 million dimension loss landscape. So they're taking like two orthogonal vectors with which to vary on, and they like do a cutout of the loss landscape in 2 dimensions. And so if you look at these numbers, what this is the poisoning coefficient. So remember I was talking about gamma, like the gamma penalty to perform well on the test set. Anyway, they showed that like when they find models that perform really poorly on the test set because they trained them to perform poorly on the test set, they occupy sharp minima. Alrighty, so actually here's where we get onto the singular model stuff. I haven't gone to the singular model stuff until now. So all right, let's go into a little bit of math. So here's basin volume, right? So actually, maybe one way we can kind of parameterize how, or we can formulate how wide a basin is we can just literally look at the volume that is within some epsilon of our current loss. So let's say our model is currently sitting at this point in weight space. We're like, okay, so like let's define this function v of epsilon. Epsilon's a very small number, as this formula. So it's an integral of all the points of loss landscape below epsilon of this prior distribution of the weights, the weights. And the prior distribution just comes from the fact that like we initialize the weights randomly, like we use a Gaussian prior. So yeah, so like if a basin is wider, it should take fewer bits to specify. Like as in the volume of this loss basin should be a larger portion of the volume of the whole weight space. And it should be more likely that we get like initialized close to it. So the number of bits it takes to specify a basin is like -log2 of the ratio of the specified volume over the total volume. And when we want to minimize the number of bits it takes to specify a particular volume. So yeah, any questions on that? This is like a little bit of information theory. We want to minimize the number of bits it takes to specify the metric. That means we want to maximize the ratio of the specified volume over the total volume. So the reason I say bits is because you can think of like the number of bits it takes to specify a volume is like if you divide your space into like a grid, like into like let's say like each bit of information. No, not really. It's like if each bit of information can specify like let's say you like cut the space in half. Each bit is like, does the weight exist in this part of the space or that part of the space? So each bit of information gives you specificity over like you can specify whether it's in one half or the other half. So it gives you like twice as much specificity, if that makes sense. And so actually, yeah, maybe I shouldn't be talking about bits. But actually, the reason I talked about bits is because in Occam's razor, you're like algorithms with fewer bits are like more likely, and use Kolmogorov complexity and the Solomonoff prior. Okay, I think I might be going too far into the math now, but yeah. So we just want to like find basins that are that have like high V, high volume. That's good. Wideness, it turns out in real models does not equal low curvature. So what a lot of people do, what like people used to do, is they would like look at this point and they would use the Hessian, which is the local second derivative, to calculate like a parabolic approximator of the local loss landscape around it. And then they would use this like parabolic approximation to say that like, okay, the surrounding loss landscape, like V of epsilon, is like something squared plus something plus like. And it turns out that real loss landscapes are not like nice and parabolic like this. Real loss landscapes look like this. They look terrible. Like this is like not a nice function. And basically when you take the Hessian, you're like, oh, the local slope is like basically zero. Like the curvature is basically zero. And then you assume that like it's extremely large when it actually isn't. So these kinds of parabolic methods break down. But it actually turns out that like in the real world, these kind of singular points in the loss landscape actually show us something very cool. So actually, let me define what a singularity is in math. It's not like a singularity in physics. Singularity is a point at which a given mathematical object is not defined, or a point where the mathematical object ceases to be well behaved in some particular way, such as lacking differentiability or analyticity. But basically, the singular points here, we define them as singular points because their Hessians are not well defined. So they're like, it's hard to take the local second derivative because the curvature is not the same as like like it's like kind of weird in all directions, basically. So that's why it's called singular learning theory. So let me get into this thing called the learning coefficient. So this is really, really cool. The learning coefficient is the volume scaling exponent. And we showed that like actually when we have like real models sitting in these kinds of like singular basins actually have way more volume than they're expected to have. And so here, like let's imagine like a regular convex basin. Um, Lambda is d over 2. So the equation we're using here is v of epsilon, the volume of epsilon that exists below epsilon difference from the off of like yeah from our current loss. As epsilon approaches 0, should roughly be proportional to some constant times epsilon to the power of uh, of lambda. Yeah. And lambda is the learning coefficient. Inside Watanabe's book, he calls it the real log canonical threshold, which is a mouthful. From here on out, we will either say RLCT or we will say local learning coefficient. But let's call it the learning coefficient. So basically, what the learning coefficient tells us is as the learning coefficient gets smaller, then our volume scale, like our volume becomes greater. Can you think of why? So in this equation, as lambda becomes smaller, the volume becomes greater. It's because epsilon is almost 0, so it's below 1. So if you imagine 0.01 to like a small to a smaller value. Wait, let me just show you this example. So a smaller lambda, like for example, if lambda is 25 instead of lambda being 50, 0.01 to the power of 25 is way bigger than 0.01 to the power of 50, right? Because 0.01 to the power of 50 is some extremely small number, and this is only a mildly small number. And so, yeah, so like basically, as lambda decreases, the volume increases. Any questions on this? No, epsilon here is the permissible gap between the top of like epsilon is the distance, the vertical distance here. So epsilon is like how much volume is between my current loss and my loss plus this value. Yeah. Sorry, I realized I kind of like went quickly over the last few parts because I wanted to get to this part that kind of explains everything. So I wanted to kind of go back and ask if anyone had any questions. I know there's probably a lot. Yeah.
So, it's sort of related thing to be like, okay, we have this testing thing. How is that anything useful? Fun fact: the first author of the diffusion transformers paper, William Peebles, and also one of the first authors of the open explorer paper, his claim to fame back in 20, claim to fame, like UC Spotlight, was this paper where he managed to like disentangle GANs lasers, like it's very very nice to disentangle, and like one direction, like for example, will affect a bunch of different vector pictures and like in the exact same way. And the way he managed to do it is very simple: the Hessian penalty. Basically, all he said is, while we're training GAN network, let's add an additional regularizer where we are trying to decrease the overall like Hessian curvature over model weights. And by doing so, because we're decreasing the Hessian, what you're essentially doing is you're saying, I want the curvature to be flatter. So even in these like much more complicated models, there is like empirical evidence to show that a lower Hessian model weight generally will lead to more generalized and kind of smoother, more interpretable like model spaces and stuff like that.
Oh, interesting.
Yeah. Oh, it's like that's one editor.
That's crazy.
Yeah. Show yeah, yeah. It's called the Hessian penalty, a weak fire for unsupervised. So like Hessians are fun, and people sometimes use it. Hessians, yeah, they're doing an approximation because Hessians did take this derivative twice, and then like goes at O into it's really slow, but then there's a lot of like statistical techniques like
Yeah, especially if it applies like a training penalty.
because you're What you're basically doing is you're doing automatic differentiation on the process of doing automatic differentiation, and you're doing every weight with respect to every single other weight, and that's bad. Don't stop for the faint of heart, and you will probably your GPU will cry.
Yeah, it's unfortunate. Wait, that's really interesting. I didn't know that. I guess that makes a lot of sense. Like you probably want to like basically this like smoothness penalty does make your loss landscape like nicer. But yeah, so as I was talking about, for regular convex models, lambda is always equivalent to d, which is the dimension of the model divided by 2. And so you might imagine why so basically the volume in this area is just like the dimensionality of the model divided by 2, because this is the exponents, and yeah, it's just like the normal volume for information. But for singular models, it turns out lambda can be significantly smaller than the model dimension divided by 2. And so what this means is that like what I mean by singular model is it turns out neural networks are singular models. So everything I've been describing for these like convex models, like all these nice drawings I've been showing you so far, this is not actually what a loss landscape for a neural network looks like. Actually, if you take cross sections of the loss landscape, it does look convex, but it does turn out there like even the singular loss landscape here looks convex if you take a cross section of it. It just turns out that there's like a lot of these weird little folds inside your loss spaces. So we can see that like for singular models, aka for deep neural networks, for anything that like isn't a Bayesian classifier, for example, it turns out that you can have like it turns out that near loss basins you often get things like this, and then it turns out that the volume in the bottom of like the loss basin is like way larger than what even like the previous papers would predict. So it actually shows you that like this even strengthens the argument that we should expect models to generalize, because more general it turns out that like because the bottom of these pits tends to be singular, they have like a lot of volume. And so here's a quote from Jesse Kuglin, like one of the researchers in SLT. There's exponentially more volume in the immediate vicinity of degenerate critical points than in the vicinity of non-degenerate critical points. And that just basically says what I said there. And so this is effectively an Occam's razor. So the intuition for like, I'll show some graphs afterwards. But the intuition for phase transitions is let's imagine you have a landscape that has a bunch of minima, and it turns out that the term that dominates for like the volume of that minima is not actually the radius anymore. It turns out the radius is, like the effect of the radius actually pales to the effect of the learning coefficient. And so let's say like you have a minima that is highly degenerate, aka it's got like a lot of folds. The more folds it has, the larger the volume is, like exponentially larger.
Wait, why?
I think visually it's hard to get intuition because these are all plus in R3, right?
Yeah.
But in like higher dimensions, they just have like a lot more volume. Just based on this equation, I guess maybe that's like the best way to explain it. As like lambda decreases, like epsilon approaches 0, right? So like let's say lambda is like half as great. Then when this is an extremely small number, then this volume is like almost infinitely larger than this volume. Lambda is the way you calculate it is really hard, but you can empirically estimate it.
What is it?
What it's defined as is how it's a scaling exponent for the volume. Generally, the more degenerate your model, the higher, the lower lambda is. So more degenerate as in it's more foldy. It's like less convex and it's got like many more of these like ridges. Or ridges? Yeah. Yeah. Yeah, kind of. Yeah. So basically, the more degenerate, I think the more degenerate means that like the more. Actually, I actually can't say this, but I want to say that like the more degenerate models have like more intersecting lines, but I don't actually know if that's the math behind it. but it does seem that like, yeah, the more degenerate means that the effective dimensionality of your model is lower. Like basically, it doesn't matter how you vary your weights. If you vary, for example, one weight positively and another weight negatively, then it will not change the performance or the outcome of your model, right? It'll still be implementing the same function. So in many cases, there are like many dimensions in which like varying the weights in that dimension won't change anything at all in terms of the loss. And so it generally turns out that like in very degenerate spaces, the effective dimensionality of your loss landscape is very low. There are only a few directions in which you can manipulate your weights such that their loss actually decreases. And so like the more degenerate your space, the more it kind of looks like this. And just like visually, it seems that in R3 there's more volume, but I actually don't know how this intuition transfers to like higher dimensional spaces. Yes. Or it's more likely for a model to fall into that space because it's got larger volume. Yes.
Okay.
You love to be degenerate. If you're a deep neural network, that is. Yeah, basically. Okay. Like as in, like if you vary weights in many different ways, your loss stays invariant. Yeah. And it's not necessarily a good place to be, it's just a very likely place for a model to be. Not really, actually. It turns out that for singular models, it's like more general algorithms tend to actually be less degenerate. But it turns out that like, yeah, I know it's a. Yeah. No, actually, it turns out what happens is it's very. Let me go forward a slide. So actually, it turns out that like many basins look like this with like many parts. So it's like you have like a less degenerate basin as part of a more degenerate basin. Yeah. Just like empirically, like I would like to like claim that there's like a simple story, but the story is not too simple. Um, but, okay. Anyway, it turns out that we do have like this effective Occam's razor, but the Occam's razor does not prefer simpler algorithms in the way we define it. The Occam's razor that happens when we train a neural network is it prefers more degenerate spaces. So when we train a neural network, all things being equal, it's way more likely that the model will end up in a space that's more degenerate, aka it's simpler according to negative lambda. Where if we define like, or sorry, it's simpler according to lambda. If we define lambda as complexity, low lambda is good. Low lambda is more degenerate. So yeah. The degeneracy of the basin is not too tied to like how well it generalizes, but generally like solutions that are better on the train set are in less degenerate basins. Yes. Yes. Yeah. Let me.
Okay.
Yeah.
So why do we care about degeneracy if it doesn't seem to affect anything? What does it affect? Why do we care about it?
It affects both train and test performance. I'll talk about it. But I just wanted to kind of get intuition of like what lambda is effectively. So you can think of lambda as effectively, we call it the learning coefficient. You can think of it as model function complexity. So like the greater the lambda, the more complex the function is implementing, and the more unlikely it is for the model to fall into that space. So it is unlikely for falling smaller. That's right. Yeah. So it's like unlikely for a model to like. Okay. So here's what Hooglin says. Jesse Hooglin says if there's a landscape with two local minima, one has like this W2 minima has lower loss, but let's say that W2 minima has higher complexity. Then solution one is simpler with higher loss, and solution two is more accurate but also more complex. It's pretty likely that actually what will happen is that the model will go into solution one, and if solution two is a subset of solution one, like if the weight space in W2 is like inside the weight space for W1, then it'll first go into W1 and then it'll go into W2. And yeah, so here's what learning kind of looks like, and here's an illustration. So recall that our volume scaling factor is this equation. As the loss gets lower, we tighten our bound and eliminate whole classes of solutions that cannot implement the sufficiently complex algorithm. And so what I mean is, like there's like the landscape kind of looks like this. So you have like this very large volume, like highly degenerate area here, and then you have this like less degenerate but lower volume area here that is like connected to it, or is part of like the more degenerate area. And then what happens is that your model will kind of traverse this highly degenerate area until it like drops into like the very small space that contains a specific solution. And so you'll see what happens is that the ball will just like, let's say the ball starts up here, right? It's just like moving, just like moving over here. And then for a long time, you see like no drop in the loss. You're like, what the heck is happening? And then very suddenly it drops into this lower basin and the loss improves a lot. And so this is called phase change. And yeah, and then let's say we're in this phase and then we want to get better. It's less degenerate, it's less foldy. It's hard to see in this diagram, I guess. I guess the upper area doesn't look that foldy either. It doesn't necessarily traverse, it doesn't randomly traverse the space. It kind of like moves towards the less degenerate space at a slow pace.
Lower?
Yes. Yeah. Yeah. Less degenerate spaces are smaller in volume and they have lower loss. The gradient points towards more, but there is like very hard to specify. No, it's not that we go towards bigger basin. It's more we're more likely to start near a bigger basin, and we're more likely to like find a bigger basin when we're like walking around, assuming there's some noise in the data set. Yeah, usually you have smaller basins inside bigger basins. These less, yes. Yes. This is this is very complex, and it is also active research. This is I believe published 2 months ago. Yes. Wait, did I say something to the contrary? Oh.
So why do less both
I think there's a good theoretical justification for it, but I don't know it.
Okay.
Yeah.
But we know that's the case.
We know that's the case in here.
Yeah. So basically what this is saying is a lot of these less complex basins, aka less foldy basins,
they're more complex.
More complex.
Yeah, they like more algorithms means less degenerate.
Got it. Okay. Okay, I can see why. Okay. So these less degenerate algorithms are usually part of more degenerate spaces.
Yes.
So okay, we start with what's degenerate basis. And we want to open the model which stumbles upon.
Not stumbles upon. It will make its way.
It will always make its way there.
Generally, there's like it's like an attractor. There's like some attraction towards the narrow part. Yeah. It's like a noisy attractor. So if it's like, usually the volume of the specific algorithm is small compared to the volume of like general algorithm. Like, sorry, well by specific algorithm I mean like small part of weight space. Generally what happens is, let's imagine you have an algorithm that is, I guess more complex, right? It's a more complex algorithm, so it's got more moving parts. If it's got more moving parts, then that means there's more ways for you to mess it up, and there's more directions in weight space which will increase your loss. I guess there's also more directions in weight space that can decrease your loss. So. Maybe that's not good to show. MXE.
Wait, so you're saying the attractors are these small smooth spaces, just less degenerate? Are they the attractors?
Yeah. So the lowest loss points are the attractors. Yeah, but the points with higher loss are widely larger in volume, and they're more degenerate.
how do you get to
No, we want to be at the bottom of the basin. That's lowest loss. Yeah. But no, like the bottom of the basin is not degenerate. Like not very degenerate. This part of the basin, the upper part. Yeah. The bottom is less degenerate. It's more specific. It's a smaller volume and usually implements a more complex algorithm. Yes. So yes. So no. Yes. Yes. Yeah. Yeah.
the one thing?
Wait, Leon? Um, yeah, how does this turn into the double descent thing is a good question. Generally, I guess as you train further, you probably reach, I don't know, actually, that's a good question. Yeah, I guess I don't have a good intuition for that.
Like it like does this and like drops a little bit, every time you know decrease the learning rate by tenfold.
Yeah.
Is the act of in that case decreasing learning rates kind of encouraging the model to go towards a less degenerate basin?
Yeah, so if you imagine these less degenerate basins or more specific basins are smaller in volume, then they're like basically if you vary your weights too much, you'll jump out of them, right? So if you take smaller steps, you can basically have lower energy. So if you like always take big steps, it's very likely you'll never be able to land this basin. But if you take small steps, you can step into it. Yeah, it's smaller in terms of like it's less degenerate. But yeah, actually, I guess that's a good question. You would think so, I guess. Yeah. So yeah, to explicitly say what I guess you guys have been very perceptively getting at. So in Watanabe's book, he formulates this thing called widely applicable Bayesian information criterion, WBIC. There's no A. It should be called LAVIC, but I guess that sounds bad. But basically, there's two terms. So here's like the shortest version of it I can find. There's the loss, and then there's the complexity. And so what we try to do is we minimize this free energy, basically. We want to push down on the inaccuracy, we want to push down loss. I also want to push down complexity. And in here, in this function, n is the size of our data set. And so what happens when n becomes very large? Well, then you see the log n term becomes relatively small compared to the n term. So as n gets very large, as our data set gets larger and larger, we like prefer having more complex models. We prefer having models with large lambda instead of, sorry, what did I say? Oh yeah. Like basically the as n gets very large, this term becomes small compared to this term. And so we care a lot about minimizing inaccuracy compared to how much we care about minimizing complexity. So lambda here can get fairly large, and it won't like penalize us that much. But if our loss is high, because n gets very large, it penalizes us a lot. If that kind of makes sense. Yeah. Yeah. Yes. Yeah, and it shows you how like the optimal solution, like basically how the optimal trade-off differs as the size of your data set increases. So as the size of your data set increases, basically the trade-off goes towards I prefer more accurate models and more complex models. So like and like minimizing inaccuracy starts dominating the WBIC because as n gets large, the ratio of n to log n gets large, right? So you care less about complexity. No, you actually prefer more complex models that have better loss. Basically, if you try to minimize WBIC on a small data set, you actually care about model complexity. Yeah, but with a large data set, you care less about model complexity, you care a lot more about minimizing the loss. Yeah. This is not something we minimize explicitly. This is what we minimize implicitly when we do SGD, because we randomly initialize the weight somewhere. And so we can think about complexity as it's just like way less likely for the model to occupy a small volume of space than it is to be in a larger volume of space. And so Watanabe kind of formulates this using the same ideas as like thermodynamics, where he's like, in thermodynamics, how like more chaotic arrangements of states are more likely, and thus when you cool things down, you kind of start from like a more entropic state and you get to like a less entropic state that's more ordered. You actually have, I don't know, more complexity, like the molecules are more specific, but like they also have better enthalpy or something. Actually, I don't understand thermodynamics too well, so. But yeah, this is what Watanabe says when he means that like training deep neural networks is equivalent to refrigeration. Yeah. Not really. It just turns out that like when we're training a model, we kind of implicitly minimize this number. This is just like some theoretical number that like it turns out we're actually minimizing when we try to minimize the loss, and we initialize randomly. The complexity here is the learning coefficient, but you can kind of think of it as like how much optimization power do you need to direct towards your model to move it from a randomly initialized point to a very specific point. You can think about it takes like a lot of bits of information to like kind of tell your model to do that, yeah, it's way more likely to have these bits of information if your data set is large. Actually, so what we'll see is that, so here, lambda is not something you calculate for the whole loss landscape. Lambda refers to the local learning coefficient around where the model's weights currently are. So let's say the model's current position is over here, right? If the model's position over here is over here, then lambda is probably low because it's like very degenerate around the model's current position. Like if the model is over here, then lambda is probably higher because it is less degenerate. Recall that lower lambda means more volume. Yeah, sorry. More degenerate. Less bits. Yeah, less bits equals larger volume because it's less specific. No, not really. It's just likely to fall into that. Yeah. Maxine?
Wait, so you said this is like something that kind of are like underlying like if any sort of like is that what you're getting at? They're trying to like loss like this underlying. It's kind of like almost like an alternate interpretation.
Yeah, we can think about like this is like what we're kind of doing at a macro scale when we're doing SGD. I think he proved this criterion is true for like ReLU models in particular. Yeah, I think Niket was talking about it, and then I saw another paper that I was reading like later in the afternoon. So we don't know whether this thing is actually correct for real neural networks we implement, like that aren't just all ReLU deep neural networks. But it turns out that it is. So there's just like this is really cool paper. Anyway, okay. So here I copied over some slides from my McIntyre talk. So I said grokking was a mystery. And
What's wrong?
Oh yeah, grokking is so like let's say you train a model from to like do something very algorithmic, like something, yeah, like a mod division task, like Niket was talking about. So let's say you train the model to predict like addition mod 5 or something, and you train it, and very quickly, like this is on a log scale by the way, so this looks sharp. It's actually not that sharp. Very quickly, the model learns to memorize the data set, and after a while, the train loss will approach 100%, and the test loss will be at 0%. This is assuming your data set is fixed, so you're not generating new samples. Anyway, at like a certain point, your test loss also becomes low. Your test accuracy becomes high. So it's like the model kind of just groks the correct algorithm, it just like suddenly learns the general algorithm. And like this is an example of what is called a phase transition. So we see phase transitions in model learning all the time. Here's an example of a phase transition from induction heads. But it's very common that like models will like suddenly form circuits that like cause their loss to get much lower, and it'll drop suddenly. So like the training graph isn't smooth necessarily. It's very common for at least large models to like you have like long periods where loss stays stagnant and then you have a sudden drop. Like Jordan was saying, this sometimes happens when you lower your learning rate as well. Basically, Jesse Hoogland claims that these phase transitions can be explained by the fact that we've dropped from this like less degenerate space, this more degenerate space, this less degenerate space. So like we've kind of gone down this steep cliff and we've fallen here, and now we're stuck in this like better solution space that has lower loss. I don't know how he explains the fact that this also applies for test loss. I think he probably has a good explanation, but I'm not proficient enough in single learning theory to explain why. So yeah, but actually the cool thing about phase transitions is we know that like as the training set is like after loss is really low for the training set, we know that the model is still building components of the general circuit. So here's what's called here's an ablation graph. So basically here's like the ablation of like how bad the model performance, like this is like how bad the model performance gets if you get rid of one of its components. And we know that like the components for the model, like basically these components that generate are already being built even before the grok. So here's the grok, right? You see like the test error go down a lot. You use the log scale, so it actually goes down a lot. But you can see that like we're building all these components that are necessary for the tests thing to generalize model. So these are actually components. I think it's part components of the residual. Like basically, if you ablate this direction, this is how much its loss goes. So we know that the way they implement modular arithmetic in the residual stream is they represent each number as vectors around a circle, and like basically if you go around a circle however many times, like you'll find the mod, right? Like let's say like you put like 5, 10, 15 as like all the same vector on the same circle, then basically 5 is the representation for 5 is equivalent to the representation for 10 is equivalent to the representation for 15, and that allows you to do mod really easily. And so here, like basically, it's like what happens if we ablate this vector direction? I think this is like one of the 5 things that models learns. So like basically they ablate that direction, and it turns out that the model field direction. But like when the model is memorized, it does not represent numbers on a circle. So like basically what I'm saying is that like as the model overfits, initially like it doesn't give a crap about circle, but even before it implements like the test, it already starts the numbers. It gets more and more important when you get a component that so here's the really cool part. So it turns out that like we make all these theoretical predictions and they actually hold up in the real world empirically. So we say like there's like this learning coefficient. Well, can we estimate it for real models? We can. Yeah, so here's the estimated learning coefficient, and here's the calculated learning coefficient, and we can see we can estimate learning coefficients for models as large as 100 million parameters, and probably greater. This line holds up very well. And we see here is on the blue line on the y-axis is training loss, and here is the learning coefficient. And so the learning coefficient increases, aka gamma increases, gamma increases, the space becomes less degenerate, the volume decreases as the model drops in loss. So this is very cool. Actually, one thing you can figure out is actually I might be wrong. This is just like, but like the increase in the learning coefficient happens like very slightly shortly before the loss drops. So you can actually even predict when the loss is going to drop. But yeah, this is like an empirical verification of the theory, and you can see like you can basically just have this all this training, and you can just take a look at the learning coefficient to kind of understand how narrow these currently are in. And so actually the cool thing is that this paper's first author is Zach Furman. And if you guys are part of ASAP, Zach Furman will be giving a Q&A on this paper tomorrow.
Ooh.
So yeah, at 1:30 p.m. if you guys are down. Show up at the ASAP place at 12 if you guys are interested. Oh yeah, this is good. This is like the fact that we can empirically verify our theoretical predictions to that degree of fidelity is exactly what we want to see. So this probably has some merit. Oh yeah, okay, so here's my attempt to kind of going back to double descent. This is not any theoretical work, so basically take this as hearsay. But the worst generalization error occurs when the model is just complex enough to fit the data set. When the param count is roughly around n, which is the number of training samples. So here, roughly to give you guys, to illustrate what I was talking about earlier, you see that when the degree of the polynomial is, for example, is 50, or this is not a degree of polynomial. I think this is like a non-linear model. But when there's 50 parameters and there's like less than 50 data points, it goes crazy. When there's fewer parameters than data points, it looks fine. And when there are way more parameters than data points, it actually is even better. And yeah, it doesn't go crazy off the end as well. So it seems that it's picked up on patterns that like the simple model has not, and it also doesn't go crazy in between the data points. So yeah, so when the model is barely complex enough, it has no complexity slack. This is just my intuition, could be wrong. In smaller models, the generalizable solution is highly non-degenerate. So in smaller models, like the low-loss solutions are like the low-loss generalizable solutions occupy such a small area of the weight space that like it's really hard to find them. And basically, what I was talking about is, yeah, no, actually, okay. Sorry, and as models get larger, it is possible that like their like most complex algorithms can be implemented in a space that is still somewhat degenerate. In the sense that like there's still large volumes of free basically variation. Like if a space is degenerate, that means there's still many model parameters that you can vary without destroying the solution. And if you have a very large model, it is very likely that you'll be in a space like you can implement an algorithm and you can still have very many parameters that don't actually matter that much. And so that means you can kind of think of this as redundancy, basically. And so you can actually think about larger models as being able to implement more complex algorithms more simply and still have more redundant neurons left over. Whereas smaller models will have the struggle to implement complex algorithms, and basically it's just like very unlikely it'll stumble into a space where like all the weights are kind of important. And so Artina, remember you were talking about like basically scaling laws and how far you can go with small models. I think it is true that like the amount of redundancy is important because as a larger model has like more redundancy. Sorry, I hit that accidentally. As a model has more redundancy, the spaces in which it can implement better solutions are more degenerate. Okay, it's more likely to fall into those areas. So it's easier for a larger model to learn the same function as a small model. What? It's yeah. I think you'll learn, or you'll be able to maneuver into that part of weight space with less training time. I think that's why like as you scale like basically we know that chinchilla optimal requires you to have a model that's like obviously way more complex than is required to implement your algorithm, right? Like, or I guess we don't know that necessarily, but like we know that Llama 7B can almost achieve the performance of like GPT-3, which is 175B, but it is trained not nearly as much. So we can think about the 175B model as having a lot more redundancy, and therefore it's like the space that contains the solution that the 175B model reached is like has way more volume than the space that the 7B model needs to reach to like calculate the same solution. Yeah. Yeah, so like I guess that what that means is I think the smallest possible model that can implement an algorithm is probably not the model that you will find the algorithm on when you train it. It'll just take so much training time to like search for that area, right? So yeah, I think that's my intuition.
and makes it like
Just answer, yeah, I think what you can say is that like degeneracy is good in the sense that more degenerate solutions are easier to reach. And I think for like a given model complexity, better solutions are like lower degeneracy. So like degeneracy is good, and we wish that like good solutions existed in high degeneracy spaces, but they don't. Um, like it's easy to be degenerate. It's hard to be not degenerate.
okay.
But like if you're bigger, you're like the solutions exist at a higher level of degeneracy. Like you can be more degenerate and you can still function basically if your brain is bigger.
Wait.
But like if your mind like if you have more parameters,
Yeah.
then you can be more degenerate and still implement the same solution and still implement the same loss basically.
So the reason I say this is like when you have more parameters, you're able to implement the same solution when it's more generic, but you also have more parameters. So it's like proportionally speaking, that's still a very like the solution trying to implement still a very non-degenerate basin, right? It's like
Oh, yeah, that's a good question actually. Now that I think about it, I don't know if the I don't
it's something to do with like the
yeah, 'cause
exponential thing where like I don't know.
I think it's possible that like the even in the cases where your loss landscape is even higher dimensional, like the lambda term here might dominate. But I'm not sure. I haven't gone through the math. Yeah, sorry. Yes. I want to say, I want to say that in the 7B model, it takes more bits to specify the same solution because it is a smaller partition of the 7B weight space. Um, yeah. Yes. Just like when it
So it doesn't even go through the whole data set. Yeah, it's crazy.
No, actually no. I remember Llama 2 in the report they said they trained for 2 epochs, and that was like an anomaly in the space. Do you know how they were able to find all the tokens? I thought there was only like, oh, I guess there's like 100 trillion. That's true. Is there like is it multimodal or is it like okay, okay. Surprising. Um, awesome. Yeah, I guess now's the time for questions. That's the end of my talk. Oh yeah, actually, introduce first. Okay, questions first.
Yeah.
I think you got the intuition, yes.
Yeah.
Yeah. Yeah.
So it sounds like there could be two options for training. So yeah, like, you can either have a really large model that finds the basic interaction, or sorry, the general solution, or you can just have an ensemble of a lot of really small models and hope and that was like correct base. Are those like equivalent?
I don't know about ensembles, but like for a larger model, you can find this like an equivalent loss solution to a lower loss, to like a lower parameter model with like less search. Yeah. So I would say that's like a, sorry, I think I'm mixing the terms like general in the sense that like a solution is general because it's an algorithm that can be applied to like data beyond the training set, and general as in there's like many solutions that are possible. Like it's like a broad basin basically. So like generally for larger models, like pretty good solutions exist in like even highly degenerate basins, like large volume basins. And you can think about for like the fact for like large models we're like really, really below their point of optimality. So if you think about like the really like if we push a model to like the edge of its performance, we can find like these like tiny volume loss basins, like all the way at the bottom, right? We can push from here to here to here. But like the tiny loss basin has really low volume. So for a large model, like maybe even a good solution can exist here. Like all you have to do is fall into this basin. But like for a really small model, the same to achieve this. So you need to search to a smaller space. Yeah. Yeah. More flops per backprop.
Yeah. So is it still easier to train larger models? Can you say anything about the fact that the models themselves become larger signal with backprop?
Yeah, exactly. Actually, this is where the chinchilla
scale.
Yeah, the chinchilla paper shows like learning curves, and it shows that actually, so there's like a trade-off, right? It's kind of like if you have a given training budget, like if you have a model that's larger, then it'll take like more compute to update it once, but it will also be a larger basin, so it'll be like you need fewer steps to search if you have a larger model, but it'll take more cost to search once. And there's like a minimum, right, that you can find. And it turns out that like GPT-3 was actually parameterized beyond the minimum, so it was more parameterized than like it should have been for optimal compute. But actually nowadays we don't really care about optimal compute. Training compute is not actually the biggest issue. We care about inference compute. Yeah. That's true. That's true. If you really want to get the most performance out of your model, you probably want to follow the chinchilla scaling papers. But I mean, you're probably going to be using pre-trained models, right? So it doesn't actually matter too much. Yeah.
Hello, okay. Well, what's this? Renew social. There's boba there. I don't know who made this. Probably Jordan. So not next week. I'm planning it for the week after. So week 6, we're gonna experiment. I'm gonna see how we're gonna do it. But we're gonna try doing like a not lecture. This isn't a reading group. It's more like presenter, right? So it's gonna be maybe you arrange the tables in a circle. I want to figure it out. Maybe we're gonna have like a 10-minute presentation on like how to read papers in general, and then we're gonna like maybe get in the Socratic seminar circle, and like if people have papers they want to talk about, we maybe read it for like 5 minutes, talk about it or something. I don't know, but like a more chill kind of just sit and like.
I don't think food is.
Okay, yeah, no, food knows after.
Oh,
I'm saying like
okay.
after, then we can go. Also, we can end earlier-ish as well, and then we can go like to Westwood and get boba. So that's another incentive to just socialize. It's a social hangout thing and a reason to get together and read papers, because I feel like people read papers on their own, but then it's just like a nice time to. I don't know how it's gonna be organized, but not next week. The week after, week 6, whatever day that is. Midterms. That's why I don't want to do week 5. Yeah. Woo! Yeah, that's my group. Thank you.